In IOTA tutorial 6, I have explained why you should not reuse an address for outgoing transactions by using the Lamport one-time signature scheme. That was a simplified explanation, but not an accurate one. This tutorial will provide you the correct answer. In IOTA tutorial 16, I have never explained why the bundle hash is normalized. In this tutorial, I will explain why this is needed. I assume that you have watched IOTA tutorial 8, cryptographic sponge construction, IOTA tutorial 9.1, key, digest and address, IOTA tutorial 10, transaction and bundle, IOTA tutorial 15, bundleHash, IOTA tutorial 16, normalizedBundleHash, and IOTA tutorial 17, create and validate a signature. If you have not watched these videos, you probably will not understand this tutorial. I highly recommend that you first watch these tutorials. To be on the same page, in the following slides I will give you a quick refresher. What is a transaction bundle and transaction objects? What is a bundle hash and how it is created? What is a normalized bundle hash and how it is created? How to calculate the number of hashes? How to create and validate a signature fragment? And how is an address calculated? So let's start with the transaction bundle. This is a transaction bundle, and this transaction bundle consists of multiple transaction objects, as you can see over here. This transaction bundle is represented by this square in the triangle. Let's zoom in into one transaction object. This is an example of a transaction object. It has a bundle hash. Each transaction object in the same transaction bundle has the same bundle hash. Let's see how the bundle hash is created. The bundle transaction object addresses, values, obsolete tags, timestamps, current indexes, and last indexes are used to calculate the bundle essences. This is the code to calculate the bundle essence. A transaction bundle consists of multiple transaction objects. Each transaction object has an address, value, obsolete tag, timestamp, current index, and last index. For each transaction object, the corresponding bundle essence is calculated. This is transaction object 0, and this is its calculated bundle essence. We do the same for each transaction object. We use the cryptographic sponge construction to absorb the bundle essences and squeeze the hash. The hash is converted to trytes and we get the bundle hash. The bundle hash is the same for all transaction objects in the same transaction bundle. The normalized bundle hash is created by extracting the bundle hash from the transaction object, and the bundle hash is then normalized. The normalized bundle hash contains no tryte value m, and the weights of the trytes are evenly distributed. You can think of normalizing the bundle hash as balancing a seesaw, by manipulating its weight to reach a more equilibrium state. This is the situation before normalizing, and this is the situation after normalizing. The normalized bundle hash is used to create or validate a signature. This is the bundle hash. The bundle hash is this bundle hash, and this bundle hash is the same in all transaction objects in the same transaction bundle, as you can see here. This is the corresponding normalized bundle hash. Each tryte value of the normalized bundle hash is converted to its corresponding decimal value. To create a signature fragment, you need to apply this calculation. This value k is the number of times to hash each segment to create a signature fragment. For example, 13 minus minus 12 is 25, 13 minus minus 7 is 20, 13 minus 12 is 1, etc. To validate a signature fragment, you need to apply this calculation. This value k is the number of times to hash each segment to validate the signature fragment. These values are calculated as follows. 13 plus minus 12 is 1, 13 plus minus 7 is 6, 13 plus 12 is 25, etc. Please note, if you add these two values together, it's always 26. These two values together is always 26. These two values together is always 26, etc. To create a signature fragment, you take the key and you hash each segment k number of times. For example, this segment is hashed 20 times and you will get this part of the signature fragment. This signature fragment is this signature fragment. This signature fragment is in the transaction object where IOTAs are spent from, as indicated by this negative value. In this example, 1 IOTA is spent from this address. To validate a signature fragment, you hash each segment k number of times. 27 segments together forms a key fragment. Hash it, you will get the digest, and if you hash this digest, you will get the address. This address must match the address where you spent the IOTAs from. This is the address where you spent IOTAs from. Please remember, this number and this number always equals 26. 1 plus 25 is 26, 23 plus 3 is 26, etc. And how is an IOTA address calculated? You take the key, each segment is hashed 26 times. You combine 27 segments together, which forms a key fragment. Each key fragment is hashed one time to get the digest. The digest is hashed one time to get the address. And this is how an IOTA address is calculated. This number 26 is the same as these two values added together. That was the quick refresher. Now let's answer the question, why is normalized bundle hash needed? I have created a simple value transaction. I have used security level 1 and transferred 1 IOTA from address A to B, and there is no remainder. The corresponding transaction bundle can be found at this location. The transaction bundle has two transaction objects. This transaction object and this transaction object. The first transaction object contains the recipient address and the amount of IOTA sent to this recipient address. The second transaction object sends 1 IOTA from this address, and this is the signature fragment. I have already explained this, but I will do it again. This is the signature fragment. This signature fragment is stored in the bundle. Each segment is hashed k number of times. 27 segments together forms a key fragment. If we hash the key fragment one time, we get the digest. And if we hash the digest one time, we get the address. This address must match the address where you spent IOTAs from. Let's assume the submitted transaction bundle is pending and a hacker called Eve gets hold of this transaction bundle. Eve can change the transaction bundle by replacing the recipient's address with her own address. By doing so, the bundle hash changes, which means the normalized bundle hash and the number of hashes are also changed accordingly. This is the transaction bundle Eve gets hold of. This is the recipient address. Eve replaces this address with her own address. But if Eve replaces this address with her own address, this bundle hash will change. Why? In this example, our transaction bundle consists of two transaction objects. Each transaction object has an address, value, obsolete tag, timestamp, current index, and last index. Alice made changes to the first transaction object. Because Alice has replaced the address with her own address, the first transaction object is changed, which means the corresponding bundle essence is also changed. If this bundle essence is changed, this value is also changed. which means the bundle hash is changed. If the bundle hash is changed, the normalized bundle hash is changed. And if the normalized bundle hash is changed, the decimal values are also changed, which means the value k, which represents the number of hashes, is also changed. So to recap, the signature fragment is not changed, but the number of hashes are changed. These are the original values, these are the new values. But if you change these values, the key fragment is changed. And if the key fragment is changed, the address is also changed. And this address does not match the sender's address. So Eve's hack attempt will fail. How can Eve be successful? Eve knows she can only make changes to the signature fragment, and she can also make changes to these k values. But these changes must be done in such a way that the resulting keyframe is always the same as the original keyframe, because you always must end with the sender's address. To understand Eve's next hack attempt, you first need to understand the following. This data is hashed 5 times to get the hash result D5. You can also draw it this way. Data is hashed 1 time to get the result D1. D1 is again hashed 1 time to get the result D2. D2 is again hashed 1 time to get the result D3. D3 is hashed 1 time to get the result D4. And D4 is hashed 1 time to get the result D5. Question: can you hash a value 3 times to get D5? The answer is yes, if you start with D2. If you start with D2, you hash it 3 times. 1, 2, 3. You get the result D5. Question: can you hash a value 6 times to get D5? The answer: no, you can't. A hash algorithm is a one-way function. It is not possible to get result D5 by hashing D more than 5 times. Another example. Data D is hashed 5 times and you get hash results D5. Question: can you hash a value 1 time to get D5? Yes, if you start with value D4. If you start with value D4 and you hash it 1 time, you get hash value D5. Question: can you hash a value 4 times to get D5? Yes, if you start with value D1. If you start with value D1 and hash it 4 times, you get hash value D5. Question: can you hash a value 7 times to get D5? Answer: no, you can't. If you hash a value more than 5 times, you'll never get hash result D5. Okay, let's see how Eve prepares for her next hack attempt. As mentioned earlier, Eve knows she can change the signature fragment. This signature fragment, where IOTAs are spent from. Let's focus on this segment. This segment was hashed originally 6 times to get this part of the key fragment. But after Eve changed the address, this hacked k value changed from 6 to 2. The original value was 6, but she needs this value to be 2. This is possible by hashing this segment 4 times. This is the segment which is already hashed 4 times, and if she hashes this value another 2 times, she gets the same output as the original situation. Let's do another example. Let's focus on this segment. This is the original number of hashes, as can be seen over here. But after Eve changes the address, the value changes from 25 to 13. Again, this is the original situation, but Alice wants this value to be changed to 13. This is only possible if the original segment is hashed 12 times, as indicated here. This hash value is already hashed 12 times, and by hashing it another 13 times, you get the same result as the original situation. However, Eve is not successful because this segment and this segment cannot be changed. As mentioned earlier, Eve still has a problem with the first and last segment. Her attempt is only successful if all k original values, these values, are bigger or equal than the corresponding k hacked values. She is only successful with this segment and this segment, but not with this segment and this segment. Now let's assume the following case. The k original values are all between 14 and 26, and the k hacked values are all between 1 and 13. In this case, Eve can successfully hack the transaction bundle and send IOTAs to her address. This is another situation. The k original values are all between 14 and 26, and the k hacked values are all between 1 and 13. This segment is already hashed 8 times. This segment is already hashed 11 times. This segment is already hashed 12 times. And this segment is already hashed 2 times. 8 plus 9 is 17, which match this original value. 11 plus 2 is 13, which match this value. 12 plus 13 is 25, which match this value. And 2 plus 12 is 14, which match this value. This hacked signature fragment and hacked k values gives the same key fragment result as the original situation. This is the bundle hash. This is the normalized bundle hash. Each tryte value is converted to its corresponding decimal value. For each of these decimal values, we apply this calculation, which results in these values. These values represent the number of hashes needed to hash each segment to validate the signature fragment. The previous mentioned decimal values, meaning the normalized bundle hash tryte values converted to decimal values, are in the range -13 to 13 and are evenly distributed just like a seesaw. As you can see over here, this is before normalizing and this is after normalizing. By distributing these values evenly, the k original values are spread. You will have low values from 1 to 13 and high values between 14 and 26. You cannot have only k original values between 14 and 26. The normalized bundle hash prevents this. By applying the normalized bundle hash, prevents Eve to be successful in her hack attempt. Now I will give you a better explanation why you should not reuse an address for outgoing transactions. Let's assume you create 2 outgoing transactions using the same address. This represents the first transaction bundle from the transaction object where IOTAs are spent from. This represents the second transaction bundle from the transaction object where IOTAs are spent from. As you can see over here, the signature fragments differ and also these hash values differ. But the key fragments are the same, the digests are the same, and the addresses are the same. Eve has found these 2 transaction bundles using the same address A for outgoing transactions. A few days later, Eve noticed 500 IOTAs were sent to address A. Eve tries a hack attempt. She takes the second transaction bundle. From the receiver transaction object, she changed the recipient address with her own address and changed the recipient value to 500 IOTAs. Next, from the sender's transaction object, she changed the spending value to 500 IOTAs. By doing so, the bundle hash, the normalized bundle hash, and the k values are changed. This is from the first transaction bundle. This is from the second transaction bundle. Eve takes this second transaction bundle as start point and she modifies this second transaction bundle. After she has made changes to the transaction object, these are the new k hacked values and these are the k original values, as you can see over here. Eve tries to modify the signature fragment. She can successfully modify this segment and this segment. If she hashed this segment 2 times, and if she has this value additional 18 times, she gets the same k value. She does the same with this segment, if she hashed this segment 11 times. If this hashed value is hashed another 10 times, she will get this original value. However, Eve cannot successfully change this segment and this segment. So by using this second transaction bundle, Eve is not successful in her hack attempt. However, there is still another transaction bundle available. So this was her first hack attempt. She only needs to focus on this segment and this segment using this transaction bundle. Let's look at this hack attempt. This segment is this segment. Eve needs this k value, but this k value is the same as this value, so she doesn't need to change anything to this segment. Next, she looks at this segment. She needs to hash this segment 12 times, but the original value is 25. So this segment needs to be hashed 13 times. And if she hashes this value additional 12 times, she gets this original value back. So by using the first and the second transaction bundle, Eve's hack attempt is successful. If you reuse an address for outgoing addresses, you provide a hacker more possibilities to successfully create a modified transaction bundle, sending IOTAs from the victim's address to the hacker's address. Reusing an address for outgoing transaction does not mean the hacker will immediately succeed in its hack attempt, but it will definitely increase its chances. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them.